Yeah, there's a subcommittee I haven't gone to this year, but if they have questions, they can always just in case. Okay. All right, great. Yeah, you're the only person wearing a tie, so you always sit tie. It's a good thing. So you stand out constantly. So let's get started. Welcome back, everyone. Just quick looking at the schedule again. The reminder: the locality sensitive hashing homework is due on Wednesday. So I'm hoping this one should actually be lighter than the last two. For those who've done, does that seem about right? Yep. So good. Okay. So this one, there are questions about some of the things that I've asked you. Usually, it's because you're thinking it's harder than it actually has to be. So there shouldn't be anything that I think is inherently too hard here. And I've not asked something quite like the bonus question before, so I don't know exactly how it's going to turn out. But I want to give you an opportunity, kind of a structured way to try and experiment with this. So then the next thing is that and hopefully on Wednesday the clustering homework will be posted. That one's almost ready. And probably by Wednesday's class you should be able to you should be prepared to do most of it. Yeah.
One question about Morse. On the Canvas, I noticed that if you go to assignments, they actually have all the assignments for the whole semester.
Yeah.
Are they relevant? I can start looking at them already, or just going to be changing them?
Oh yeah. So usually I don't have the actual PDF link to those yet, and I will update those assignments in Canvas usually with the link to the PDF and also the source at the time that they're available.
So if you click the link, it's not going to go get you anywhere.
So I mean, you'll have a description that's empty. So you can kind of see where the dates are and start planning ahead. Okay, so the other important thing that's coming up is the data collection report for the project. So this afternoon we've finally unmuted the feedback for the proposals. So sorry for the delay on that. So the good news is most of the proposals were fine. There weren't any issues. A few of you, I asked you to kind of, I had Madia put a note to to come talk to me. So it's usually easier to do this face to face. That way, it's over email. It's better to have more of a back and forth. So just try and find a time. Before, after class, or office hours are the best time. If that doesn't work, let me know. We can figure something else out over email. So the reason for having the proposal so earlier, I want you to kind of start thinking about your project, and as we go through the class, you're thinking, oh, maybe I can apply this on there, right? So they're not like things that are set in stone. You can revise them as you want. If it's a big revision, you should kind of so check with me and Madia, but otherwise, feel free to kind of add on things that you're discovering as we go. The next deadline, which is a week from Wednesday, is the data collection report. Okay, so this is, if you click on here, it links to the PDF of the project for the project, and so this is not meant to be kind of a big assignment. It's worth 10 points out of the 100 points total on the project. And basically, if you write down pretty reasonable answers for these 5 parts, you're going to get all 10 points, right? This is something I have to keep you moving on the project, so you're not waiting till the very end, okay? But I do want to give you something constructive to actually do. You should be thinking about where you're going to get your data from. Some of you in your proposals had this kind of written clearly. You had a good idea. Others of you were more vague. I want you to try and nail this down at this point. Okay, so that's kind of one of the most important things. And if you want to change it, or you come up and you get feedback from us that you should also try someplace else, that's also fine. Okay. If you remember, there was a bunch of links that good places to start here, but this should not be limited. Okay, so feel free to look elsewhere as well. So it should be at most 1 page. Okay, don't make it super small font or super small margins, anything like that. You know, one group, just 1 page. And so, okay, so the other important thing I want you to think about, the first is try and download your data set, right? Okay, number 2, think about not just, okay, I've got this data on a file somewhere and this is how much the file size is. But start trying to think about how you're going to put it in some abstract data type, like you're going to represent it as vectors, or as a matrix, or as a graph, or as sets in some way. Okay, this is what I want you to start thinking about now. You might change this answer, but I want you to make an attempt at how you're going to do it. For some of you, hopefully you'll get a chance to try and pre-process the data into one of these formats up to this point, okay? If that's going to be pretty complex and you think that will take up a larger bulk of your assignment, you know, you say, we've started to do this, but this is something we're working on. That's possibly okay too, okay? But I want you to have a concrete plan if that's the case. You may say, I'm going to try out a few different values of K in the K-grams or something like that, okay? So, that's kind of the most important, the 2 most important points I want from you at this stage. I think that should be reasonable at this point in the class. Okay, after the intermediate report, I'll give you much more directed feedback at that point. Okay, but this will just kind of keep you moving. The question which is the most, and so kind of what format, I don't just want the file format, I want kind of thoughts about the abstract representation. Okay, the most confusing part though is probably step 5. I ask you, how would you simulate so similar data? Okay, this is kind of an open-ended question. It's a question where I'm trying to get you to think. There's not necessarily a right or a wrong answer, okay? But I want you to think about this and kind of think, is there an underlying model which is generating this data in somehow? If I were to be able to press a button and it generates a random data point and then do this several thousand times, could I get something that could act as a proxy for what I want to do? Okay, and maybe this is not the full raw data, but it's the abstract data that you're working with. But you want it to kind of follow some pattern. So this is often super useful in 2 ways. Sometimes the actual data you have is limited and smaller than you'd like to demonstrate your techniques on. So you only have access to smaller data set now, but you want to see how it scales up. If you simulate data well, you simulate a lot of data, and then you can see how it scales up. Okay. Another reason it's important is when you're thinking about how you generate it, this is kind of implying something about the underlying model, right? If generation kind of tells you, okay, that's kind of determining what the structure is. There's not always a generative model for all sorts of data, but I'd like you to try and think about whether there is or not. Okay, so it's kind of open-ended question, but you should kind of think about it and kind of have fun. This is a good way to kind of move you forward analyzing what you're doing for your projects. Okay, any general questions about this? So that's a week and a half. You still have some time. So great. Okay, so we're starting. Great. So we're starting clustering today, and so and specifically we're going to look at a type of clustering called hierarchical agglomerative clustering, and so this is kind of one of the 3 major topics we'll cover in this course. There are, say, thousands of types of clustering. Okay, so there are tons and tons of variants of clustering, and there's not really kind of the notions of this counts as a clustering algorithm and this doesn't is even hard to put a boundary on. It changes with the type of data you have. It changes with what you want to do with it. We're not going to try and be exhaustive here. Okay, so in this course, so occasionally, so Suresh Venkata Subramanian will teach a course just on clustering, a full semester on this topic. We're going to have roughly 3 lectures, and then there'll be a lecture at the end on graphs, which is somewhat similar to clustering again at the very end of the semester. All right. So in this lecture, we're going to cover, or in this series of 3 lectures, we're going to cover 3 types. So the hierarchical agglomerative clustering, which I'll explain. Then we're going to talk about these so assignment-based clustering. And if you've heard of k-means clustering, then this is the prototypical formulation of the assignment-based. But there are other variants as well that we'll cover, and they'll be different than if, say, you took the Foundations of Data Analysis course. And then the third one we'll talk about is going to be spectral clustering. So spectral clustering is going to use a matrix or a graph formulation of it, but you can apply it to data points as well. These 2 formulations, the hierarchical agglomerative is going to actually form some hierarchy in between the clusterings. So I'm going to have more structure here. The spectral will also form a hierarchy between the clusterings. The hierarchical agglomerative, the agglomerative, if you haven't heard that word before, I don't know if I've heard it outside this context. You might guess what it means. It means you kind of agglomerate, or you kind of glue stuff together. So it's going to be building it from the bottom up. The spectral is going to be top down. It's going to be splitting the data over and over again. Okay, and then the assignment base will just be finding representative points, and then everything else is defined as a result of that. So we'll go through all of these, but this is kind of the setup for the next 3 lectures. Okay. So then the most maybe the most important point I want you to get away is I've pre-written up here. When data is easily clusterable, then most clustering algorithms, whatever you choose, is going to work quickly and well, with the exception of some hierarchical stuff, which is inherently slow. And when the data is not easily clusterable, then no algorithm is going to be able to discover clusters which are not in the data. Okay, so I'm covering these three variants here, and this probably, what I'll cover is probably at least 90% of what people use for in clustering algorithms. These are the main built-in ones. There's some other specialty things, and there's some differences around the edges. But for the most part, if the data really has a bunch of these different subsets of points which are distinct from each other and grouped together, then most algorithms will find them, right? There's not some inherent difference in the kind of the general overall goal here. But there are some differences on certain cases, and so we'll go through those. And there are differences in, depending on your data is, how you define a similarity or a distance. It may make some of these techniques available and otherwise they're not available. Or they give you a hierarchy or they don't give you a hierarchy. Or they give you a representation of the data which is compressed or they don't. These seems to be more of the difference than one works. I have this data, k-means formulation gave me a good clustering, but hierarchical did not find a clustering. That's very rare for that to happen. Okay, it's more like the secondary aspects of these techniques that is going to be more important. Okay, so I also want to draw kind of a data. The basic idea with clustering, you get these data points. Okay, so I get some data here. Each data point is from some set X. Okay, so each one of these points, so this X here might correspond with one of these data points. Okay, and then in order for me to do to perform clustering, I need a distance that's right. So some distance defined on this data, or maybe a superset of the data. Okay, so I need to have some distance formulation here. I have some data and a distance formulation. So this is why we need to talk so much about distances. The difference between different distances is going to kind of make an effect on how the clustering works. You can sometimes you can use a similarity instead of a distance. Okay, and we'll kind of see these small differences throughout the lectures. Okay, and so then once you have kind of a distance and a data set, the clustering kind of in general is going to be subsets. In this case, let's say there are 3 subsets of X, so that S1 union S2 union S3 is equal to X. And so typically you say Si intersect Sj is equal to the empty set. So there's no intersection. So it's a partition of the data into different parts. In this case, 3 parts here. And probably I would say S1, S2, and S3. Okay, so there are 3 parts of the data. I want to put each data point into one of these partitions. This would be a clustering. Okay. So this is the basic goal. Now I could have done something different, right? You would look at this data set I've drawn up here, and you think, okay, so if the data is drawn this way, this is clearly the way to divide up this data set. So why is this? So why was this the obvious way to break up the data set? Or I'm sorry, maybe you don't think this is the obvious way to do it.
The distance between points in the clusters is small, and the distance between any points, like among different clusters, is large.
Yeah, so good. So there are these 2 kind of characteristics that we can try and think about, which are useful for evaluating why this is a good clustering, right? So this formulation what I've written here doesn't tell you anything about what is a good clustering, but we need to kind of add something on it. So there are these 2 parts that generally you want to try to have some optimization that deals with at least one and hopefully both of these parts. You want the intercluster distance. I want this to be small, right? So for all, let's say x1, x2 in Sj, I want the distance xi or x1, x2 to be small, right? So I want all the distances between 2 points in the same cluster to be small. Okay, that seems reasonable. And then the other part is if I pick the intra-cluster distance. So I want this to be large. So for xi in Si and xj in Sj, for I not equal to j, I want dxi xj to be large. Okay, so I want the distance between points in different clusters to be large if possible. Okay, so these are kind of the 2 intuitive notions that you can do. And so hopefully these 2 kind of concepts make sense, but there's probably still kind of vague. How you formalize this is extremely varied. Okay, so there are lots of ways, and we're going to kind of go through some of the ways to approach this. Okay, but these 2 properties seem reasonable, right? If 2 points are in the same cluster, hopefully, given the distance, this is part of the formulation, right? So the distance, then the distance should be small between them. And if they're in different clusters, you want it to be large, right? So that's the basic properties that you want. Okay, and there are differences. So sometimes the clusters do not need to be actually disjoint from each other. You can make them so a point is partially in one and partially in the other. And there are all sorts of variants here. This modularity approach we'll see in, like at the very end of this semester, doesn't even force that this is that the data sets are a partition of X. It just tries to find well-grouped points. Say these points are all similar to each other, and there may be points I don't put in any cluster. Okay, so these are less common variants. Usually you follow, when you say clustering, you're talking about this. Okay, where it's a disjoint partition of the data, and within each partition you want the distances small. Across the partitions you want the distances large. Okay. Okay, and then one more thing I want to say on this picture. Okay, so this picture provides great intuition and also horrible intuition for what's going on. So when your data is in 2D and looks like this, as I mentioned earlier, the best thing to do is probably to plot it and take out a pen and circle the clusters like I've done here. All right, I would not recommend running any specific algorithm. I'd recommend plotting and circling. Okay. If the real power of the algorithms we're going to talk about is that they're going to work when the data is not nicely, listed in 2D. I just need data points and I need a distance. Doesn't need to be the Euclidean distance, right? It could be one of the other distances we talked about. The data points do not need to have coordinates and embedded in 2D. Each data point could be a set, and I could use the Jacquard distance. Okay, so these formulations are going to be much more general, and this is useful when I'm not able to plot them like this, right? Okay, so when I'm not able to plot them, then I want to use clustering to really help me know what's going on. Okay, one more picture I want to draw, and every year someone tries to do a project where it involves getting some data set, and they want to run clustering algorithms on this data set, and often they show me a picture of the data, and it looks, and the data looks kind of like this. Okay, so this is a common sort of data that you would kind of see where I plotted it, say in 2D, and there's kind of a big group over here, and maybe it tails off. How many clusters would there be in this data set? Maybe one. Yeah, so not too interesting. Okay, so this goes back here. If the data is not really clusterable or there's only one cluster, nothing should find clusters in here. Okay, if you run, if you end up getting a data set like this and you run clustering on there and you tell me that there are 8 clusters in here, I'm not going to be happy. Okay, I mean, if you show a different representation of the data and you explain to me why there really are 8 clusters, okay. But if your justification is you plotted it and you ran k-means clustering until you got 8 clusters, and then you said, yep, there they are. That's I don't want you to do this after going through this class, okay? In other classes, they can teach you to do that. In this class, I don't want you to say there are clusterings in a data set that looks like this. Okay? Okay. So I'll try and revisit these points. I think these are important and as important as the actual algorithms here. Okay. So hierarchical agglomerative clustering. Okay. Okay, so this is, so remember the input here is going to be some data set and some distance d, right? So that's usually all you're given here. You might be given a number of clusters or some other sort of parameter. And so the basic algorithm is I'm just going to write this out informally. So if two points or clusters are so close enough, put them in the same cluster, and then repeat. Okay, so you're going to look through all the points or all the clusters you've already formed, and if they're going to be, if you think that they're close enough to each other, then you put them together in the same cluster, and then you keep going until you stop at some point, or you have one cluster left. Okay, and so that's basically what it's going to do, and then there are like a zillion variations of this, and we'll go through some of the more common ones. Okay.
You have clusters of clusters, and you can do nested clusters.
So you implicitly get this, but as you're running it, you just think you just have clusters. So I'll say this in a little bit more detail right now. Okay, so I'm going to start. So the 0 step is for each xi in x. I'm going to put in a separate cluster Si, right? So at the first step, if I have n data points, I have n clusters. Every cluster has 1 point in it. Okay? And then I say, while I have now I don't have data points, I just have clusters. So now while two clusters are so close enough, then I will find the so I'll find the closest pair, and let's call this Si, Sj. So this is the pair of clusters which has the smallest distance between them. And then 1b, I'm going to merge into an Si prime, which is going to be equal to the union of Si union Sj. Okay, and so this is the whole algorithm. So I've written it slightly more formally, but it's the same thing as in red here. Okay, so you think of having some data points. Okay, and so the first step is I'm going to put them all in their own cluster. So every point is its own cluster, right? Then in the next step, I'm going to essentially say some points are still close enough. These two maybe are the closest. So I'm going to put them in a cluster together. Now this cluster is a subset with 2 points in it, right? And then maybe the next closest are these two, and then maybe I decide that these two are closest, and then these, and then maybe I stop here, maybe I merge these into one supercluster. Okay, and so if I assign these letters A, B, C, actually let's put this one C, D, E, and F, then I can think of A, B, C, D, E, and F, and I'm going to kind of build this hierarchy on top here, where I'm building a hierarchy over the clusters, right? So A and B were the first to merge, then E and F, and then I merge D and E with E and F, and this gives me this big cluster right here, and similar A, B, and C are in one cluster, and so forth. Okay, so procedurally, this is how it works. All right, okay, so now that I've written this down, so there are two things I have not yet defined, and this changes the variance of this hierarchical clustering. There's one main thing that I haven't defined. Yeah. Yes, great. Great. So what I've not said are the closest pair of clusters, right? So my input here was a distance, and this is defined between the data points. And so when I start out, I just need the distance between, say, A and B. I know how to compute that. But now when I'm saying, okay, D, is D closer to A and B, or is it closer to E and F, the cluster E and F? Right? That I have not defined yet. Okay? And this gives me a lot of variance here that I can plug in different things for how to define the distance between clusters. Okay? And there's one other question we haven't answered. Yeah, go ahead.
What is close enough?
Yeah, right, good. So the other thing is, what is close enough? When do I stop? Right? When do I stop going up this hierarchy? Maybe it made sense only A and B and E and F were really close enough to group. Right? Or maybe I want to stop when there are two clusters left. I've been told I want exactly K clusters. So I did A and B, I grouped E and F, and I grouped D. So then that would mean if I said K was 3, then maybe I would stop here. So that A and B were one clustering, C was one cluster, and D, E, and F was another cluster, just because that's what was cluster when I ran it. That's how it worked in this procedure. Right? So the answer to this question, the second close enough question, is not at all clear. Okay, there's generally not a good answer. Next Wednesday it'll be, or on Wednesday maybe I'll try and give you some rules of thumb of how to approach this. Maybe the end of the lecture today. Okay, but that's really how many clusters should you have is kind of this unanswerable question. So let's talk about how do I define a distance between pairs of clusters. Okay, so distance between a pair of clusters, say S1 and S2. Okay, so who has a suggestion? So let's just open it up to the audience and see if you come up with the ones which are I've listed and ones beyond that. Yeah. So I take the average of. Okay, good. So there's a so the first whole class of these, right? This is not just one thing. Is I find a center S1 of S1 and S2 of S2. Maybe I'll write these. It's a little hard to see upper and lowercase when I write. My handwriting is not that great. So maybe I'll do C1 and C2. Okay, as the centers of these two clusters. I think you mentioned the average, right? And so then I say the distance between S1 and S2 is equal to let me write this distance, an uppercase distance. So this is now the distance between C1 and C2. Okay, so if I'm given a lowercase d, that's part of the input somehow. And it's a modeling choice again. But as I've given lowercase d, then I can define uppercase d in this way. But then how do I compute the center? Well, one way is ci is equal to the average of si. Right? So I can take an average. It turns out that if I take the mean is defined over like Euclidean. If I have my points are Euclidean vectors, I can do a coordinate-wise average, and we'll come back to this on Wednesday. And this gives me a nice notion of average. Okay, so this is probably what you mean by average here, and this is a common formulation that will link to the k-means clustering formulation we'll talk about on Wednesday. Now this is not exactly the same result here, but this is kind of a similar setting. Okay, good. So this is one reasonable choice. Any other suggestions?
I have a suggestion for distance between clusters. Or the
Sure. Yep.
So basically, building out of this assumption right here, if we have an average, we can basically say that one cluster is going to be a perfect circle, and whatever is on the edge of the circle will be the farthest point from the center. And so if the next point, the distance from the center to the next point is farther than from the center to the edge of the circle, then it's going to be another cluster.
Sure. Okay. So good. So this is another formulation. I'll try and write in this context. It will actually, the thing you're thinking about will be more natural. What we'll talk about so slightly later. So how I define this distance would be so the right. So you, someone want to say that the distance between S1 and S2 is equal to the radius of the min enclosing ball of S1 union S2. Okay, so I take S1 and S2 to these two clusters. Okay, they're nicely here, and I find the minimum enclosing ball that contains both of them, and then I look at the radius of this ball. Okay, and this can define a distance in between these two clusters, S1 and S2. Okay, so this is another reasonable one. This will be really linked to another formulation we'll see soon. Okay, any other?
Take all pairwise distances between each of the points in each of the clusters, and the minimum of that is defined as the distance between the two clusters.
Yeah, so this is probably the most common formulation of hierarchical agglomerative clustering. And this is going to be equal to the min over all x1 in S1, x2 in S2, the distance between x1, x2. Right, so I look at all pairs across the two clusterings, the two clusters as input, and I find the minimum of all these, and I take that distance, right? So this is called single link. Okay, and so this actually is a neat formulation that is pretty distinct from a lot of other forms of clustering. And this was the one that kind of sets hierarchical agglomerative clustering apart, in that this can find certain types of clustering that others can't. Okay, and I always feel bad if I draw this, but you can get a data set called that's so that's called the two moons data set, and you can find these where they're kind of two moons linked together, and if you do this form of clustering, what you'll do is you'll end up linking them together like this in one cluster, and you'll get S1, S2. You'll find this clustering where these are all, each point only has to be close to one other point in order to be linked together. And so otherwise, this point by itself, it's closer to a lot of these points than this one, but you argue it fits more naturally in this sort of data set. Okay, and so a lot of other formulations of clustering will not find this type of pattern. The reason I hesitate to put this up here is I've looked, and I don't know if I've ever seen a real data set that looks like this. I know people who've worked in this area, and they've worked very hard to find these topological constraints between points that where a data set where this would actually make sense. And so it's pretty rare. So one thing you might get is if you have like GPS coordinates of someone walking here and someone else walking, that you link these together. But probably then you kind of know whose GPS coordinates are whose, right? So that's, if you don't know that, then this works unless they cross over each other, and then you're kind of in trouble again. So I mean, there are some cases where you might see this, but this will give you something that's very structurally different than this distance here. This distance here would have this point kind of close to a bunch of these points in some way. Okay, so this single link formulation is kind of neat and gives you this neat structure like this. So great. Any other variants? This is a good time to get your class participation points. You know what percentage of your grade that is? Okay, great.
This kind of you can use one point as a representative of the entire cluster, like the point that is closest to the origin, for example, and then you just are restricted by 2 points.
Yeah, so there's more options within this first category here, right? So you proposed, let's CI equals, let's say arg min of x in SI of just the norm. If I just take the norm, whichever minimize the one closest to the origin, I find some canonical point here, right? And so this might work as well as any other point. Unless my data points are, if I use this and my data points are all unit vectors, then they're all going to have the same thing. But but if it's another data set, maybe this is useful. This one maybe is more stable to use the one closer to the origin. The furthest from the origin, I know in certain data sets is actually is associated with having the most information associated with it, and then that becomes maybe a good representative. Yeah.
Average the min and the max, that might approximate some kind of center of gravity.
Yeah, right. So there are lots of ways you can create some sort of center of gravity or some representation. You could find the argmin, take the argmax, and if it's Euclidean data, then you can take an average of those 2 points. So that's another reasonable thing. Yeah.
I don't know if this overlaps with some of the other ones, but taking every point and putting a ball around it, and every time there's overlap, then we consider them the same cluster.
Okay, so this is this would be similar to a formulation I'll mention at the end of the lecture today. I don't know how to write a distance between that because I want to fix within this kind of restricted. This is really a restriction of clustering. I need to define the minimum, and you just gave me kind of a binary value. It's either there. I should link them or I shouldn't. If the balls overlap, but that would be a reasonable thing to do, and we'll see. I'll mention quickly this dbScan algorithm, which essentially inherently uses this as the core of their formulation. Yeah, in the back.
Is there any use to try to build functions or build functions through the clusters and comparing functions?
Sure. Okay. So what you're thinking of now is build like a generative model on both S1, S2, and the union of them, and then compare like the overall likelihoods of these models. Is that what you're thinking? Yeah. So then compare likelihoods of S1, S2, say, and likelihood of S1 union S2. And maybe if the overall, some likelihood score of some modeling of some function describing the data is a good enough fit for S1 union S2, or it's the smallest one out of all choices of merging them, then I can take this as my next merge. Right? So this is a reasonable thing to do, and this will actually correlate with a mixture of Gaussian's approach to clustering, which I will hopefully mention at the end of Wednesday's lecture. Okay. One more. Yep.
Yeah, to find the centers, we can use the median.
Yeah. So so this is an interesting point. So C1 equals something like the median of SI. Okay, so the point here would be that a median, the reason someone would use this over like an average would be that it's often more robust to outliers. We'll come back to that, I think, more on Wednesday, and I think you might see something in your homework on examining this. The problem is that a median is, I know how to define the median in 1 dimension. In 2 dimensions, how do you define the median? So ranking in what? So one thing you can do is you can, in every individual dimension, assuming you have Euclidean vectors, is you can take the median in those dimensions, and then that each of those gives you one of the d coordinates. Right? This is a thing that is a not uncommon thing to think. This formulation actually does not have very good properties for like robustness. It may not be in what's called the convex hull of the data set, which means that I can draw like the smallest convex shape that contains all the data points, and the point you may have implied does not necessarily need to be inside of that. So the median in high dimensions is a tricky thing. So there's the common formulation of this is actually, and there are many variants of the median in high dimensions, and some of them are quite reasonable. The simplest to think about, I'll think, is the argmin of x, let's say restricting this to RD, that minimizes the sum of, well, let's call this C here. That minimizes the sum of all the distances. C. Okay, so minimizes the sum. So the mean, the average, is not what does that. The mean minimizes the sum of all the squared distances. And the L1 median might be what the names for this object, minimize the sum of the distances. Okay, so this is more robust to outliers. In Euclidean distance, there is not a closed form solution for this necessarily, unfortunately. You can approximate it well and so forth, but there's not, for the average, I know how to take the average. That ends up being simple. The median is less clear how to do that. So instead of doing this, sometimes instead of over all of our D, I would cross this out, and I will say I'll only consider points in the data set. So now you can check every point in the data set to see if that's a good representative. And we'll come back to this on Wednesday. Okay, this will also correspond with another common class. All right, so I think I just want to mention okay, so I want to mention a couple more variants here. I can replace this min operation with instead, this can be instead, I can take the average of all distances instead of the minimum distance. Or I can also take something like the max of all pairwise distances. Okay? Max is often associated with is often called the complete link. So I want all of the distances between the pairs of points to be small. That's different than the smallest minimum closing ball radius. Those give you slightly different answers. Okay, they're similar, but they're not exactly the same. The average pairwise distance, I compute all pairwise distances and I average them. This is going to be similar to taking the average between the centers. This one, in the moment I'm not confident, but I think these might actually end up being the same in Euclidean distance. So the average might end up being the same as the representative center. But I'm not 100% confident on the spot now. But so there are variants in here as well. So Okay, so a lot of you came up with your own clustering variants. There have been dozens, at least, papers written on everything that was mentioned here. By any of you, maybe even hundreds or thousands of papers on various of these variants. You can choose what you want here. Okay. So which one should you choose? So which variant should you choose? I'm not. It's one of the points where I'm not trying to give you an answer. I just want you to think how would you decide?
Well, like if you logically think about that, you probably choose the one which provides the proper clustering across all different types of sets and with like low margin of error.
Sure. So how do you so good. So this is the right way to think about it. But how do you know what's the proper clustering? What do you mean by proper? And so how do you measure error? Right. So if you can measure some error of the right answer, then yeah. So one thing you'd like to do is gives the proper clustering, and this means the smallest error. So you can think of, for every clustering variant I had some distance that I defined, and I said when I get to, say, there are only 10 clusters left, or whatever value k clusters left, I can say this one gave me the smallest total distance at that point, but that corresponded with the distance I chose as my modeling, right? So it's tricky.
Yeah, probably then to be more specific, we can say that the best variant is the one where the distance between all the clusters is always greater than the distance between points within each cluster.
So good. I mean, this is exactly the right things to be thinking, but again, which distance you used in order to define this? I still needed a choice of how to measure this. And so essentially what's going on is each of these variants corresponds with some choice of what you want to optimize. Right? So you're thinking exactly the right thing. You would have chosen this distance or that distance because you're like, actually, this seems like the most useful thing. I end up going to put a ball around each of the clusters, and I want those radiuses to be small. So this is what I want to optimize. Or I want to have a representative for each cluster, and I want the sum of the distances to the representative to be small. So then I need this median variant of it. So you're exactly thinking the right thing. So however you want to measure the error, however that matters to you, and whatever you're going to use the clusters for, well, that should help inform you on which variant to use. Right? So you kind of need to be thinking about this and choosing the variant. If you want clusters that look like this because you think data points that are close should be really close to each other, then you might want to use this single link variant. Right? So that one is distinctive in that way. Right? But it depends on how you want to measure the error. Right? And these are tricky questions to answer, and I can't tell you which is the right one. The right one depends on the task that you're going to be using these for. Yeah.
So what you're saying is there's no formalized method for choosing the right clustering algorithm. It's just an art.
Yeah, it's an art. Yep. So yeah, maybe you thought this was a class that was going to be kind of founded in like there's right and wrong, but it's an art class. Yes. Yeah, so choosing a cluster and choosing how many to choose is, often referred to as like a dark art, because it's how people make these decisions is often messy, and you often you hope it works, but try and really justify it. If I keep you're doing a good job of trying to come up with answers, but someone like me can come around and always poke holes in it, right? I've been on, defenses for PhDs where someone proposes this, and then you say, well, what about this? And they're like, I hadn't thought about that, right? So,
So does that relate to practical applications like self-driving, for example, machine learning, where 90% of the cases are really, you can go through them fast and get them into the groups and analyze them, but then those outliers, those last 0.1% or 1% is the most difficult one to follow.
sure. So, right. So you're asking how does this fit into like these applications like self-driving cars, where some parts of it are easy, right? Like, this thing. If when the data is clusterable, you can do a lot of stuff. It's the harm cases that really there's a little difference around the edges there. So like classification, where you can say this is like a supervised variant of learning, where you kind of can evaluate whether answer was good or bad, right? You can say, this time the car crashed, this time it hit someone while driving, and this time it didn't. I want the one where it didn't hit someone, right? You can kind of, if there's kind of a good metric that's outside the individual formulation, which tells you how to evaluate. Clustering, these things are linked together. So in general, these unsupervised learning, which clustering is part of, has this general problem that there's kind of no way to evaluate when it's doing the right thing and when it's not necessarily doing the right thing. It's typically used in cases where you're either doing exploratory data analysis, where you're trying to run a bunch of stuff and see if actually you go and pick one of these distance functions, like the sum of the distances to the center or the sum of the square distance per center, and you say, yeah, that actually looks small. That's good. There are clusters there, right? Or it doesn't look small and there aren't clusters there, right? You can kind of look at these things. What's the choice of small? That's hard to know, right? But it kind of starts to help you understand the data more. You can use it within these classification applications sometimes by saying, here's a bunch of similar things, and in this case, I can easily define, say, that I know how to solve it. And in this other case, I say this doesn't fit into any of the nice clusters. It's an outlier. Maybe the car should slow down, right? One of these things like this, right? Maybe I designed something specialized for that because it doesn't fit into this grouping. And sometimes clustering is useful for those tasks. Okay. Yeah.
So you mentioned like the exploratory stuff. Does anyone ever just randomly pick a point in a cluster to determine distance?
Sure, yep. So you can pick a random representative element. That's a perfectly good one. CI equals a random element here, right? So this works well, and we'll kind of see a variant on Wednesday that's going to do something like this. Actually, that's so this it's not as crazy as it might sound. Okay. Often, if they really are pretty nicely clusters, then a random one should be a reasonable representative. And in high dimensions, there may not be any really center one, so a random one is just as good, and it's certainly much easier.
Question. When we mentioned about which variant to choose, there was a discussion saying that probably the one which gives the smallest error. But when we actually talk about error, it's like kind of a deviation from an idealistic solution or something.
Yeah.
But how does it apply now?
Yeah, so what the error is and what the idealistic solution is defined in the same way as your distance between the clusters or how you evaluate a cluster in some way. They're kind of linked together, right? So, these, okay, so the downside about hierarchical agglomerative clustering, this framework, is that you're kind of giving this distance, which is kind of describing what you want, and then you may have some specialized way of measuring error, like this or like this in some way. Those may not line up. You may not actually get the right answer. It's a procedural definition of clustering. It's not here's a specific task I want to optimize. The ones we'll see on Wednesday are going to be the latter. We're going to say, here's specifically what I want to optimize in my clustering, and then here's a shortcut to how to do it that doesn't go through this hierarchical approach.
In some domains, is it reasonable to decide a priori what the number of clusters should be and let that drive the choice of distance?
So I think these are kind of separate questions. They're equally hard questions that, so, you know, if knowing that I only wanted 3 clusters may not tell me how I wanted to cluster them. You know, there are formulations of clustering where I want to get every clustering essential. I mean, you probably wouldn't call this clustering, but you can do procedures where every subset is going to have a diverse set of points in it. Okay, so the clustering might be A, D, and F would be a good clustering, and B, C, and E would be a good clustering, and those would be 2 clusters, where these would be 2 clusters. They're solving inherently different problems, right? This diversity is good when I want multiple different representations of my entire data set, right? They usually wouldn't call it clustering, but it kind of fits into the similar sort of framework up until I just described the cost function, right? So it's just knowing how many I want doesn't necessarily give you the answer. Yeah.
Is there clustering to fit shapes, desired shapes?
Sure, yeah. So so you want each cluster to kind of fit, to look like a line segment or something like that.
Sure. Yeah, or
Yeah.
a triangle or square.
Yeah, so yeah, so we'll kind of see something like that with the mixture of Gaussians. The mixture of Gaussians we'll see on Wednesday. I'll just mention at the end of the lecture. We won't go too much in it, but it kind of fits. I mean, this fits. It tries to put a generative model on top of the data that looks like a Gaussian, but the Gaussian can execute. So this fits a particular type of shape. But you could fit a different generative model that say, I think the data, each cluster is going to come from something that looks like a triangle. And then I try and define the distance from a point to a cluster or 2 clusters by how well I can fit a triangle to the data. And so you could do something like that, yeah. This is less common, but you could do it. Okay, so good. So I want to mention, so, okay, there's one more answer here, is that which variant do I use? And so, I mean, this part of the answer to this question was, you know, the distance D is linked to error in the evaluation. But there's another kind of concern that you should have, is that the computational so complexity. Okay, so how long does it take to run? Okay, so before I answer this, let's think about, like, generically, this hierarchical agglomerative clustering framework I set up. How long would this take to run? Like, what if I had n data points? Let's say I get to a constant number of clusters, right? I might as well do all of them along with.
So I think you need to compute the pairwise distances between all points. So that would be n squared there. And then as you build the clusters, you might need to go to, like, bound it by n different iterations of those pairwise points.
Yeah.
So that'd be 12n cubed.
Nodes in. Right, so there are O of n nodes in the hierarchy. That tree I built, it's going to have linear number of nodes in it. Each of those was the result of finding the closest pair of distances. Okay? In the worst case, the first merge I do, I had to check all n squared pairs of points. Okay? And so the total runtime is actually O of n cubed. You might think, well, as I get further and further up the merge tree, the number of things I have to check is going to be smaller. But the first n over 2 of these merges, I still had n over 2 clusters, at least n over 2 clusters, and n over 2 squared distances to compute. Okay? Now, it's not, so naively, it's n cubed. Okay, now, when I go up this merge tree, a lot of those clusters, when I merge 2 of them, most of them don't change. So if I can cache the pairwise distances, then I don't necessarily need to recompute all of them. So if you're careful and I store those n squared distances in a priority queue, then I can get this down to like n squared times log n. Okay, so I can kind of fairly generically, with enough space, if I don't worry about the space, I can get this down to n squared log n. Okay, it turns out this is still slower than you'd like to be. Okay, hierarchical agglomerative clustering is typically too slow. Okay, people don't use this on large data sets. It gives you a lot of modeling power, which is kind of easy to change. I can change this uppercase D distance function between clusters, and I get different variants, the data clusters in different ways, but it's going to be kind of slow with priority queue. So people typically don't use this that much, especially for large data sets. Okay, so one aspect of the computational complexity. Oh, there's one more aspect that I even to do this, it's even a little bit trickier. I have to do n squared of these pairwise distances. Sometimes these pairwise distances are actually, I have to check all pairs within the clusters to find the minimum or the average or the maximum, and that also could have an n squared term inside there. So you have to be careful. Now it turns out you can compute this and store this once, and this ends up not, but there are other complications here. A naive implementation is going to look n cubed, and maybe it's going to look worse. Okay, so this really is kind of slow, even with some basic optimizations. So one of the things is which variant should I use is, can I make this faster? Can I make this more efficient? I want something where the scalability with n is more like linear. And like something like n log n would be good, or n times k, where k is the number of clusters. Okay, so can I get to O of n log n, or O of n times k? Okay, and so if I can do that, I say, I don't care about the variance so much. It's some modeling choice. I don't know what the right modeling is. So if I can go faster, I might as well go faster. All right, so I'm going to mention two faster variants that are kind of analogs to some of the formulations that we described earlier. Okay, so there's a mention of an algorithm called that's called dbScan. It's called for density-based clustering, and this is pretty popular. And I'm not a huge fan of it. It's got some issues with whether it converges. There's a claim that it's n log n, but that's not always true. There are variants of it that, if you're careful on how you implement various things and you allow some approximation at certain steps, you can probably get close to that. And if you search for some stuff online, you can find faster variants. But in practice, it will often work fairly well and fairly efficiently. Okay, and this is built into a lot of software packages. Okay, so this is going to need two parameters. So it's going to have your data set, it's going to have a distance, and then it's going to have two parameters associated with it. One is going to be some radius, and the other is going to be some threshold on the density. These are given weird names in the paper and Wikipedia. I think these are more natural. So how this works is I'm going to have a bunch of points. And this is really meant usually for low-dimensional Euclidean data. But you could use it in more general setting, as long as I have this distance function. Okay, so what I'm going to do is for each of the data points, I'm going to draw a ball of radius r around each of these data points. Right, so I can imagine these around they should all be the same. I didn't do a very good job here, but they should all be the same same radius. Okay, so this one here. And so if the distance is going to be symmetric, then what that means is if the ball center around this point and the ball center contains, this is A and this is B. If the ball center around A contains B, then the ball center around B contains A. Okay, so it has this nice dual property here. And so what I want to first evaluate is for each of the balls, for each ball of radius r around some data point, I want to say, I want to look at this quantity, this radius intersect my data set. And so this is now a set, right? I've written a set down here. X is a set. I intersect it with this geometric shape, the ball, and I count how many points here, right? So if I look at this ball here, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. Right? So in this example, I'm going to have 8 points inside the ball. And so I'm going to say if this quantity is greater or equal than tau, then I'm going to say that X is going to be what's called a core point. So I want to first do this operation. I do a nearest neighbor search, or find all the points nearby some data point. I can use LSH, I can use these KD trees or something else. And I want to quickly return all the nearby points for each point in the data set. Okay, this should take, if the nearest neighbor search takes log n time, then this takes roughly n log n. For each data point, I need to do this, right? So this is where the roughly n log n comes from. Okay. Now, I want to identify all the core points, and then for any pair of core points which are within a distance r, I want to link these together. And I want to say the linked core points, so link core points where the distance between, say, x and x prime is less than r. And this is going to be a cluster. Okay, so I say all these points are in the same cluster here. Okay, and if then I can identify there's some like straggling points here, which are going to be, this one itself is not core, but it's within a distance r here. So then I will add on a couple of these other points, which are within a distance r, but not part of the core. Okay, and then these are my clusters. There might be these disjoint sets, cores, which are not connected, and then I connect these nearby points. Okay, and so this is basically what the dbScan algorithm does. It's a procedure in that it runs this process and then it returns the clusters. But I don't know exactly what the formulation is, but you kind of get the sense. There's some radius. If the radius is denser than some threshold tau, I say that's a dense region and I want those points to be grouped together. Right? There are some points left over out here that were never dense enough. I'm not going to put those in a cluster. Okay, so this is pretty similar to this, I guess, this formulation where you wanted to check if there are enough dense enough points inside of a ball, right? And it's also similar to these other, it's pretty similar to like the single link algorithm, where I run the single link hierarchical clustering up to a distance r, until the distance between the clusters, again, is the minimum distance is a distance r. I link all those points together into the same cluster. Right? It's going to give a pretty similar result. They're not exactly the same. This one is reliant on core points. Maybe these two are a distance less than r, but I didn't put them in the same cluster. Right? So it's not exactly the same. I said it's either 1 or 2 outliers. I don't care whether they're 1 or 2 outliers together. Right? So it's not exactly the same, but it's pretty close to the single link, and it's going to run much faster. In a sense, I don't need to every iteration add 1 point and then redo everything again. I can kind of pre-process and do a lot of this at once. And so people often use dbScan instead because in practice it runs faster. Now, if the data set is like super dense in a region, there's like a constant fraction of the points are within the distance r of some point, then the first nearest neighbor search return is going to take n squared time to return all the points within some distance. So you need to kind of deal with these cases specially and other issues like that. They're all going to be core points. You just need to identify them quickly. So okay, so this is another variant. Okay, and then I want to tell you one more. That's going to be, we're going to go over this again on Wednesday. This is another faster variant, which is going to call, well, there's the k-center clustering. And specifically, this is going to be the Gonzalez algorithm. And this one is going to run roughly in n times k time. Yeah, so this way, if k is small, I want 3 clusters or 10 clusters. This one's going to be much faster. And I'll revisit this again tomorrow. I think this should be one of the most fundamental clustering algorithms, and I think it's under taught. Because it's so efficient, it just runs. It's so much easier to control the runtime. It works roughly as well as, almost as well as a k-means variant, you know, and as well as these single-link variants. But it doesn't give you the hierarchy. Same way dbScan, there's no hierarchy associated with this one. So to get the better runtime, you're giving up on the hierarchy. Okay, so that's also going to happen. So I'll just write down this algorithm, and then we'll go through an example, and then we'll talk about this more to start off on Wednesday. So I'm given a data set, a distance, and k, and this will work for any d which is a metric. It's going to have nice properties that we'll discuss on Wednesday. Okay, so so I'm going to and so this is the input, the output is going to be a set. We're calling these C1, C2 up to CK, and these are the centers of clusters. Okay, and I'll explain more how to think about these on Wednesday. But so I'm going to pick C1 is going to be pretty much so arbitrarily from the dataset X. So I pick an arbitrary first point. Usually you pick the first point in the file, okay? You know, but you could pick one at random. It's, you know, the properties you can prove about how well this works. It doesn't matter which point you pick the first. Okay, and then I'm going to, and then for j equals 2 to k, so I'm going to run a for loop. I'm going to say set cj equals to the arg max of x in this data set, where I'm going to say the arg min of c in c1 up to cj minus 1 of x minus c. Okay? So this is, I get an arg max and an arg, actually this I don't need an arg, so this is, yeah, so just a minimum distance. Okay, so what is this doing here? I'm saying, so this is the whole algorithm, okay? So I've written down the whole algorithm. Let me just draw a simple example here. And so this is trying to do this formulation where no data point is too far away from one of the clusters, from one of the cluster centers. Okay, so I will pick a data point here. This will be C1 arbitrarily. Okay, so the first thing I do, this is only one data point here, so I don't need to worry about this min. Okay, so then I pick the point that's argmax from C1, right? The furthest point from C1. That's going to be up here. This will be C2. That's the furthest point away. Then the third step is where you first have to see the trickiness. I want to find then to pick the C3, the furthest point away from the minimum to either of these two. Okay, so I check for every point, I take the distance to C1, I take the distance to C2, I find the minimum, and then I take the maximum over all those values, right? And so there's kind of a line through here, and it's going to be, this point will be C3. That's kind of, this is kind of like the bisector between C1 and C2, at least with Euclidean distance. You can define bisectors for any distance, actually. But so, you know, the point that's furthest away, essentially closest to the bisector, right? And then I can keep running this. The furthest, I mean, I've already found that there are kind of 3 clusters here, and I found 3 representatives, right? So this worked pretty well. This was really simple. Right? I could run this again to C4. Maybe it's this point, it's this distance, or this distance. You know, I don't know what's the smallest, but I would run till there. Okay, so this is what's called Gonzalez algorithm for the case-centered clustering problem. So this is another simple, faster variant. Okay, great. So we'll talk more about this on Wednesday. Sorry, I need to run right now to the Academic Senate, but there are a couple TAs in back, so Harshini and Sanjana will be around to answer questions.